Hello, I'm Indiana Renfro, and this is Lab 5, the following Slinky. In our table of contents, we'll have an introduction, experiment with Slinky's motion, computational modeling, model versus exponential graph, and conclusion. The purpose of this experiment was to observe the effects of gravity and the drag force on a Slinky as it is dropped. We will take the video of the Slinky and place it through the tracker app and record its motion. We will then create a computational model and compare the two. One thing to look for as we reach the results is that the bottom of the Slinky tends not to move until they reach contact with the top. The terminology and equations to keep an eye out for. The key physics principles we will see in this experiment is Newton's second law, velocity update, drag force, position update, and tension force. Here is the experiment of the Slinky's motion. As you can see, right here at the bottom is not moving. The top continues to fall with the force of gravity. And right about now, when the top hits the bottom Slinky, then it falls downwards, and you can see there's a bit of resistance with drag force we'll see later, but you can kind of off-see to the side of the y values. The y is pretty constant, but once the top hits about here, around 6 seconds, it then begins to downgrade. In part of our computational modeling, we had initial values of a ball mass of 0.22 kilograms. This is our initial vector. This is the initial x position, and here's the initial y position. There is initial velocity of 0. Our frames was 0.033 seconds. Gravity is 9.8. We have a j-hat vector of 0, 1, 0, and the drag force used is 1.88. This is the tension force, as we can see. This is about the tension of the spring as the top is falling to the bottom. That around here at the 6-second point, the 5.833, which is about the time the top hits the bottom. We even have the update for F net of the ball times gravity and j hat, the tension. Then we have the velocity update and position formulas. And then they would plot on later. And this is after the top hits the bottom, where there's drag force as the Slinky falls with gravity. We have the force of the drag force plus the ball falling. It was all total 9.2 seconds. The update formulas again. Yeah. Here's the results of the computational modeling. As you can see, around 0.437. It was constant until about right here, the 5 or 6 second mark, and it started to like linearly decrease to 0. When comparing the model and exponential graphs, here's the model as we saw on the last slide. They're both constant, but I think they're still fairly similar. But the reason why the experimental position is more longer and more steeper than the model position is because of how I had the axis set up there in the tracker. That's a possible source of error. Instead of like having the bottom as the center of origin, the center of the axis, I kind of had like the bottom of the ground. So it looks like it's coming towards 0 and then like actually showing where it's fall. So that was a possible source of error. Plus, it was kind of like hard to get like accurate experimental results. The tracker app also updated, so possible software error. And then also like human error of placing the axis along the spring. Because also when you watch the experiment video, the Slinky also kind of like moved towards the left on the x-axis. So that's part of the error conclusion, but our question is like, what does it mean? So the question was, does the bottom of the Slinky stay stationary, just like the video? I would say based on the computational models, it does. You can see the constant y position of the straight line around 5 or 6 seconds, just like the experiment. The bottom stayed stationary until the top kind of hit and applied the force. I watched more of the Slinky video, and the reason behind it is because as the force of gravity is coming down, the bottom of the Slinky is non-reactant because of how there's the normal force pushing up on it, and then the tension bouncing against gravity is like kind of equal to the point where the tension lessens and the force of gravity got stronger. which resulted when the force of gravity hit the bottom of the spring, there was less tension, and it just resulted in the bottom to fall as well. And that's about it. Thanks for listening to my presentation.